In today's video, here is a nice problem regarding arithmetic and number theory. Here is the following setup. Find all a, b, n as a non-negative integer satisfy this following equation. Okay, we get 5 to the a plus 7 to the b equals the power of 2. I just wrote this problem simultaneously, so I came up with this one. Indeed, it looks like a challenging problem to solve, but in reality isn't. Okay, because the confusion here with the factorization. Okay, even though you may prove a is a even, but we don't have another term which can help us to make a difference of two squares to factor out that. Okay, because each term here is an independent integer. Okay, as well as this one, we don't know how to factor out this one as well. You guys, you can give it a try to this problem period with the solution. Go ahead, pause this video when you worry, come back to see the full solution. Okay, now let's jump into the solution. First of all, we are going to prove the parity of these three integers. Okay, so I'm going to reduce the equation to the mod 8. Then you will immediately know what's the parity of each integer. Okay, I'm going to reduce the equation to the mod 8. Why mod 8? Because it's clearly this one, if n is superior to 3, is going to be 0. Okay, so also this one will be minus 1 to the b, and then check the mod 8 of this one. We know 5 square is always congruent to 1 mod 8, and we know 5 to the 4th is always 1 is congruent to 1 mod 8, and all the way down, if this clearly is going to give us 5 to the n is congruent to 1 mod 8. I'm going to reduce this one by using the mod 8. For all n is superior to 3, this equation becomes 5 to the a. This one becomes minus 1 all to the b, because we know 7 equals 8 minus number 1. So this one is clearly 0 mod 8, because we have 2 to the n here. If I'm going to move over this term to the right, I will have 5 to the a is congruent to minus 1. If I'm going to minus 1 here to the b here, I'm going to cancel this minus here, minus sign. I'm going to put it to the exponent, b plus 1, which is mod 8. Then using this fact, we know 5 to the 2n is congruent to 1 mod 8, because if I'm going to multiply this one by 5, I will have 5 to the 2n plus number 1 is congruent to 5 mod 8. By using this fact and this fact, it's clearly the exponent is odd here, but the remainder is 5. If you have the exponent even, the remainder is 1. It's the same thing here. You will have the same thing here. Since you get minus number 1 here, so the exponent must be even in order to get this one here. We cannot get 5, because if this is odd, you will have minus 1 plus each, you will have 7. You will have a remainder 7, which is impossible to be odd. This one must be even. If this one is even, this one also must be even, as we mentioned there. Okay, so it's clearly a must be even, and this one is even, because we get b plus number 1, thus b must be odd. Okay, let's write this information over here. So we know a is even and b is odd. Now let's erase this board and move on to the next board. This will determine the parity of a. It was even. Let's set a equals 2m. Okay, because we know that is even. We know this term is a. Now let's replace this value of a into this one to see what's giving us. So it's clearly is going to give us 5 to the 2m plus 7 to the b, which equals 2 to the n. Okay, let's use a nice trick here. We are going to apply the Fermat-Lero theorem on this one. So by Lero-Fermat theorem, if p not divides a, this implies a to the p minus number 1 is congruent to 1 mod p. Okay, let's take a equals 5 to the m with p equals 3. Okay, so this 5 to the 2m is the same as 5 to the 2m is the same as 5 to the m all is raised to the 2, which equals 5 to the m all is raised to the 3 minus number 1. Okay, it's clearly is going to be verify the Fermi-Taylor theorem, because we know 3 not divides 5 to the m. Okay, so this one is a congruent to 1 mod 3. Okay, now let's apply this one and this one here exactly. We know 5 to the 2m is a congruent to 1 mod 3. Adding this one also, we get 5 to the 2m plus 7 to the b is a congruent to 1. Also 7 is a congruent to 1 mod 3, because we know 7 is 1 more than 6. Okay, 1 is a congruent to 2 mod 3. But remember, these two terms equals 2 to the 2n. Okay, this one is telling us to the 2n is a congruent to the 2 mod 3. According to the divisibility statement, means I get 2 to the n equals 3 is multiplied by k plus number 2 as a reminder. What is a k? The sum natural numbers. Okay, now we have extracted a nice expression here. We know the left hand side of this equation is even because it's a power of 2, which means the right hand side of this equation must be even as well. How to make this one even? K must be even. So k is even, because even is multiplied by odd is still even, plus this even is going to give us even. If it's even, let's set k equals 2d. Okay, now let's take this value of k and insert it back here. So I get 2 to the n, which equals 6d plus number 2. Let's divide both sides by number 2. I get 2 to the n minus number 1, which equals 3d plus number 1. Okay, so I have extracted a nice formula here. Now let's take this one at the top and continue solving this one. Previously we have collected nice and enough information. Now we came up with this nicer results. We get 2 to the n minus number 1 equals 3d plus number 1. Okay, we need to prove this exponent is even. How to do that? I'm going to reduce the equation to the mod 3. Okay, if I'm going to do that, it's more simple. It's going to give us minus 1 all is raised to the n minus number 1 is a congruent to 1 mod 3. You might say, how I get to this one? Because we know 2 equals 3 minus number 1. Okay, 3 it's clearly is 0 when you divide it by 3. I will be left with this minus number 1 raised to the exponent n minus number 1. For the other side, this one is clearly is 0. I will be left with number 1 here. Okay, so we get this one, which means n minus number 1 must be even. If the n minus number 1 is even, we will have the same remainder, which is true. Okay, so this one immediately is going to give us n, which means n minus number 1 is even. Now let's set n minus number 1 equals 2 is multiplied by c. Okay, now let's take this value and replace it here. So I get 2 to the 2c, which equals 3d plus number 1. Then move over this number 1 to the left and factor out that on the form of the product, because we will have a difference of two squares. So this one immediately is going to give us 2 to the c minus 1 factor 2 to the c plus number 1, which equals 3d. Okay, so we have arrived at this nice expression. So what to do here? Now we are going to deal with the GCD. We know GCD of these two terms. We know the GCD of this one. GCD of these two terms equals 1, because we have a consecutive odd integers. If you replace c with number 1, you get 1, you get 3. If you replace c with number 2, I get 3, 5, 5, 7, 7, 9, and so on and so forth. The GCD of these two terms is always number 1. Now we are absolutely free to choose the appropriate value for this one, because since we found GCD equals 1, okay, we are free to go straight to the value of 3 or D for each term here, okay. Since this one is smaller than this one, which means it's going to take the small value, and the other one is going to take the big value, but we don't know which one is smaller or bigger, which means we are going to take 2 cases, okay, or 3 cases. Moreover, if 3 divides this one, which means 3 cannot divide this one, okay. So we are not going to do anything else. We are simply going to straight put this one equals this one, and the other one is going to take other value, okay. So let's do that. So we get 2 to the C minus number 1. Maybe it's going to take number 1, okay. The other value 2 to the C plus number 1 is going to take the whole thing, 3D. The other case, maybe you have 2 to the C minus number 1 is going to take number 3. The second one is going to take D, okay. Lastly, we can have 2 to the C minus number 1 equals, we can have inverse here. We can have this one equals D. The other one is going to take 3, because we don't know yet which one is smaller, which one is bigger, okay. Make sure one of the equation is an extra. Just I want to show you something here. So let's solve this equation first. We just move over this number 1 to the right. It's immediately it is going to give us 2 to the C equals 2. Thus C equals 1, okay. We found the first value. If C equals 1, now let's check this one. You may have a solution for that. So replacing number 1 here into C, it's immediately is going to give us 2. Thus N equals 3, because after you're moving over number 1 to the right, okay. So we get 5 to the A plus 7 to the B, which equals 2 to the 3, which equals 8. This 8 is going to be written as 1 plus 7. Also this one is going to be written as 5 to the 0 plus 7. Now we found the solution for this one. This 0 equals A, this 7 equals 1, okay. Now we found the first solution. We get A equals 0, B equals 1, N equals 3, okay. Now let's move on to the next equation. So this one, if I'm going to solve this equation, it simply is going to give us 2 to the C, 3 plus number 1, which is 4, is the same as 2 squared. Thus C equals 2. Here is another solution. Now since we found C equals 2, now let's replace it here. So this one is telling us N minus 1 equals 4, because after you're replacing C with number 2. Thus N equals 5. Now we found the value of N equals 5. Now let's take that value of N and insert it back into the original equation to see what's the next expression. I got 5 to the A plus 7 to the B, which equals 2 to the 5th, which equals 32. 32 is the same as 5 squared plus 7. So 5 squared is clearly is going to take A. This one is clearly is going to take B, okay. So here is the second solution. We get A equals 2 and B equals 1 with N equals 5, okay. This one, it was just an extra equation, because you will have the same thing. You get 2 to the C equals 2, C equals 1. This solution, we already found that before. We don't need to take this equation, okay. So the only 2 solutions that we found, this one, okay. So I have ended this video. Thank you for watching. I will see you next video. Bye.